Hello everyone, my name is Alberto Martin. I'm from the University of Seville, and today I will be presenting RESTest, which is our framework for black box constraint-based testing of RESTful web APIs. First, let's put a little bit of context here. So when we are doing black box web API testing, we're doing something like the following. Imagine we have the YouTube API, and first we need to generate the test cases, the inputs. So these are the HTTP requests that we are sending to the API. They will look something like this. So you have a path where you're sending the request and a method and a set of headers. And then you're obtaining a set of responses, some of which may be successful, some of which may be erroneous. And they will look something like this. So with these responses, you need to assert a number of things, whatever you prefer, and check whether the response was successful or not. The problem here that we are talking about is how to generate these inputs. So how to generate these requests, and especially for those APIs that contain a specific kind of constraint, which are interparameter dependencies. So right now you may be asking yourself, okay, what's an interparameter dependency? So here you have a few examples. This comes from the YouTube web API. In that API, you have an operation to search for videos, channels, comments, etc. And for example, you can search for videos and filter them by their duration with the video duration parameter. But the thing is that if you specify a value for this parameter, you must also set the type parameters value to video. So that's an interparameter dependency, a restriction, a constraint between two or more input parameters of the same web API operation. Here you have another example. This comes from the PayPal web API. And here you have a dependency occurring between two different properties of the same JSON body of the request. These dependencies can get as complex as you may imagine. This is an example from the Foursquare web API, where you have a dependency occurring to 5 input parameters of the same web API operation. Okay, let's start with the introduction. First thing that we're going to talk about is the OpenAPI specification. The OpenAPI specification is a language that is becoming more and more industry standard, and it allows you to describe a RESTful web API in a structured way. So you can include there the paths of the API, the operations that you can perform, and the parameters that you can use for every web API operation, for example. And the best of this language is that it is both human and machine readable. So it can be used to automate certain things like code generation or even testing. So thanks to this, there has been so many approaches in the last year for automating black box web API testing in practice. So basically what you're doing here is you're taking the OpenAPI specification of the API under test. Based on it, you are generating test cases for the web API, and you're sending those test cases, you're sending those HTTP requests to the web API, for example, the YouTube API. But the problem is still the same in here, and that is that interparameter dependencies are not supported in any web API specification language, including the OpenAPI specification. So this is an open issue from the OpenAPI repository, which has been open for more than 5 years, almost 6 years now. It has received more than 50 comments from more than 30 participants, and as you can see, many positive votes, so more than 340. So when we realized about this problem, we wanted to see if this was recurrent or not, if this was common or not. So that's why we reviewed a set of industrial APIs, so 40 APIs in total and 2,600 operations, and we found more than 600 dependencies. And we're talking about APIs like YouTube, PayPal, Amazon, etc. And one of the main conclusions that we drew is that these dependencies are extremely common and pervasive. So they appeared in 4 out of every 5 web APIs that we studied. But the best of all is that we managed to classify them in 7 patterns that you see there. This is an already published work which was presented last year, actually here at ICSOC. Now that we knew that this was a recurrent problem, we wanted to come up with a solution for specifying these dependencies and also for automatically analyzing them. And that's why we created the IDL tool suite. IDL stands for Interparameter Dependency Language. It is a domain-specific language that allows you to describe all these 7 patterns of dependencies in a succinct way. I think the syntax is mostly self-explanatory, as you can see there. We also created an open API specification extension so that you could include these dependencies directly within the open API specification document, so easing the work for developers. And finally, we also created a tool called Ideal Reasoner, which allows to automatically analyze these dependencies. So for example, to automatically generate a valid request, so as a request satisfying all dependencies, or to check whether a given API request is valid or not. So with all this previous work, we were finally able to present RESTest, our testing framework for RESTful web APIs. This is the basic workflow of RESTest, which allows you to automatically generate and execute requests for RESTful web APIs. But let's go step by step. RESTest needs as input the system model. So it follows the model-based approach, and in this case, the system model is the API specification. So the open API specification of the API under test. Based on that API specification, it automatically generates a test model. The test model includes a series of details that are necessary for testing the API, as we will see in a few moments. Now that we have the system model and the test model, we are using Ideal Reasoner to automatically analyze the dependencies of the web API. So in this case, the first thing that we are doing is we are checking whether the API specification is valid and whether there is some inconsistency among the dependencies or not. And if there is some inconsistency, if there is some error, then the execution is stopped and the user is warned about this error. Now, once we've checked that everything is correct in the system model and the test model, we automatically generate test cases for the web APIs, for the web API. And these test cases are abstract, meaning that they can be later instantiated into any given framework. In our case, we are instantiated these test cases in the Rest Assured framework, which is an extension for the JUnit testing framework. And finally, these test cases can be compiled and executed and automatically sent to the web API. And a set of test reports are automatically generated too. Now, a few details. The test model, as I said, is automatically generated, but it can be manually augmented to tailor the testing process. So you can define the operations under test. You can also include authentication data like API keys. You can use custom test data generators for specific parameters, which may need very specific input data. Imagine, for example, the YouTube API. If you need to create video IDs or to create language codes, you can create those with RESTest test data generators. And you can also include parameter weights in order to specify which input parameters you want to test more thoroughly than others. Now, how do we implement constraint-based testing in RESTest? We do it with Ideal Reasoner, and this is how it works. First, we take the API specification, and then we also take the dependencies expressed in Ideal. Then we feed both resources to Ideal Reasoner, and Ideal Reasoner automatically transforms them into a constraint satisfaction problem using a language like Minisync, which is a constraint modeling language. Now that we have the dependencies expressed as a CSP, we can automatically invoke a number of analysis operations in this problem, like this that you see here. In the context of RESTest, the operations that we are interested in are the isValid operation, which allows to check whether a given IDL specification is valid or not, and the getValidRequest and the getInvalidRequest operations, which allow you to automatically generate both valid and invalid requests to the API. So requests satisfying and violating the dependencies of the web API. Another challenge that we needed to overcome when testing RESTful APIs was what test oracles to use in an automated way. So imagine you are testing the YouTube web API, you are sending an HTTP request to it, then you are obtaining an HTTP response, and then you need to tell automatically whether that response is correct or not. And for that, we use a number of automated test oracles. First one, we check for the absence of 500 status codes, which reveal server errors. Then, since we also have an open API specification, we check the conformance of the web API with that specification. So imagine we obtain a response containing some undefined property in the OAS. then that's a conformance error because that property was not included in the specification. This is just an example. And then we also use a few oracles that are a bit more powerful in this context. So basically we check that for valid inputs sent to the API, we should obtain a successful response. So a response containing a 200 or in that range status code, and vice versa. So for invalid inputs, we should obtain client error status codes. Inputs can be invalid because of two reasons, either because you're using invalid parameter values, like for example, using a string parameter for a parameter that only accepts integers, or because you're violating one or more interparameter dependencies of the web API operation. I want to remark that in this context, these two oracles, 200 status code for valid inputs and 400 status codes for request violating interparameter dependencies, these two oracles are novel. So you can only use them if you're using our approach for automatically analyzing the dependencies. You need to know whether these dependencies are satisfied or not a priori in order to use these two automated oracles, which are novel in our proposal. Now, once you have executed the requests in RESTest, you will obtain a test report like this. So this is, for example, from the Foursquare web API, and we've been executing a number of test cases. And as you can see there, you get to see all the test suites that are generated and all the test cases that failed, organized by the kind of error that you're getting. Okay, so let's head into the evaluation. How we evaluated our approach. We wanted to evaluate the following two research questions. First one, what is the effectiveness of constraint-based testing in generating valid test cases for real-world APIs with interparameter dependencies? And second, what is the fault-finding capability of constraint-based testing in real-world APIs with interparameter dependencies? Well, regarding the case study that we used, we took 9 RESTful services from 6 web APIs used by millions of users worldwide. These APIs are Foursquare, GitHub, Stripe, Tumblr, Yelp, and YouTube. And just to give you a few more data about what these RESTful services look like, these are the general stats about them. So these services, these operations had between 5 and 31 input parameters, 14 on average. They had between 1 and 16 dependencies, 5 on average, and they had between 3 and 25 parameters involved in at least one dependency, 9 on average. This is what we wanted to do in our evaluation. We wanted to compare these two test case generation techniques, random testing and constraint-based testing. And by random testing, we mean the current state-of-the-art technique that is being used by other approaches. That is, you are generating requests by randomly assigning values to parameters. In contrast, when we do constraint-based testing in our approach, we generate the requests by using constraint solvers. So Ideal Reasoner supports a number of constraint solvers, and you're using those in order to generate the requests. Let's head into the answer to the first research question. So what is the effectiveness of CBT in generating valid test cases for this kind of APIs? This is what we did. We generated 1,000 valid requests per case study, both with random testing and with constraint-based testing. And then we actually checked which requests were valid. And by valid request here, we mean a request that satisfies all the interparameter dependencies, so all the input constraints in the web API operation. The way in which we counted these requests was by checking the 200 status code. If we received a 200 status code, so a successful response, we counted that request as valid. And this is what we obtained. With random testing, only 40% of the requests that we generated across all case studies were valid. In contrast, with constraint-based testing, all the requests that we generated were valid by default, 100% of them. Actually, this was extreme for random testing in some cases. So there are some highly constrained APIs, like some services in the Stripe and the YouTube APIs. And when you are performing random testing on those, you're only getting 1% of valid requests overall. This is extreme. And in the case of these APIs, you can get a huge improvement by using constraint-based testing, where you get 100% of valid requests by default. This is the overall stats that we got when answering the first research question. So with random testing, you get between 1 and 90% of valid requests, 40% on average. And with constraint-based testing, you get 100% of valid requests. That 97.1% that you see there is from the Yelp API, but it wasn't because it didn't generate valid requests for that 3%, but instead because these requests revealed server errors in the API. So these requests return 500 status code. That's why you see there the 97%. Regarding the time to generate 1,000 requests, you can see that random testing is faster. It only took 2 seconds to generate 1,000 requests. But with constraint-based testing, although it is true that it took around 100 seconds to generate 1,000 requests, this increment in time is negligible compared to the fact that you're generating all valid requests and that you're able to uncover more bugs in the APIs under test, as we will see now in the next slides. Okay, time to answer the second research question. Can we actually find bugs? Can we actually find failures in these APIs by using this novel constraint-based testing approach? Again, this is the settings of the experiments. We generated 1,000 valid and 1,000 invalid requests per case study. What we mean by an invalid request is a request that either violates the dependencies present in that API operation, or that uses invalid data. As I said, for example, like using a string parameter for a parameter that only accepts integer. The way in which we counted the failures was when some of the test oracles that I showed you a few slides before did not hold. In that case, we counted that as a failure. And this is the results that we obtained. So with random testing, we were able to uncover failures in 5 out of 9 services under test, but with constraint-based testing, we uncovered failures in all services under test, so 9 out of 9. So it's not possible to give you an idea of all the bugs that we were able to uncover, so I'm going to show you a few examples. This first is from the Foursquare API. This is one of the type of errors that we were able to uncover with constraint-based testing. And that is that we found several 500 status codes. So in this case, clearly the API is showing an error because it's returning an internal server error status code. This second bug is a bit more weird or awkward, let's say, and it is from the Yelp API. So in this service, when you're searching for locations or businesses in Egypt, if you're using a language like French or Italian or English, that's perfectly fine. You will get a 200 status code with a set of results. But if you use a language like Finnish or Danish, not only you will not get no results, but you will also get a 400 status code saying that the location could not be found. This is completely wrong, since this API should return at least these results in English instead of not returning anything and actually returning an error, which shouldn't happen, as we saw with our languages like French or Italian. So this third bug comes from the YouTube Web API. In this case, we were testing the comment threads service, and we basically sent a GET request to this service, and we obtained a quite shocking error in the response. We obtained that 400 status code telling us to check the request body to ensure that it was valid, although no request body was included, and so this bug becomes hard to debug. For a full collection of the bugs that we found with this technique, you can go to the supplementary material of the paper and check all of them. And these are the overall stats that we obtained when answering the second research question. So with random testing, we found between 0 and 1,200 bugs, failures, in the services, so 300 on average. And with constraint-based testing, we found between 10 and 1,500 failures and 500 on average. So as a conclusion, I would like to remark that this problem of interparameter dependencies is very common. So as we saw, these dependencies, these constraints are present in 4 out of every 5 web APIs, and we're talking about common APIs like YouTube, PayPal, Flickr, etc. So based on this, we wanted to come up with a way to automatically test these APIs, so automatically generate requests that satisfied these interparameter dependencies. And that's why we created RESTest, our testing framework for RESTful web APIs, which allows you to generate valid requests for these APIs automatically. We demonstrated this by performing a number of experiments, and we showed how we could generate 100 valid requests for APIs containing interparameter dependencies, as compared to 40% of random testing on average, and even 1% in some APIs like YouTube and Stripe. And thanks to this, we were able to uncover a number of bugs in services like Yelp, YouTube, Foursquare, Tumblr, etc. So this would be all. Thanks a lot for listening, and I will be welcoming any question that you may want to ask or anything that you may want to discuss about.